Hello, my name is Joshua Bengio, and I welcome you to this presentation for the Samsung AI Forum. Welcome to the forum. I will give you a presentation on causal representation. Hello. Um, so today I will work with you on ideas that have been making progress in our community about causality and learning representations that can capture how the world works, which I believe are related to how humans understand the world and how they could use that understanding to reason in a conscious way. So to get us started on this topic, I think it's good to try to consider the sort of thoughts we have, sort of knowledge we manipulate with our thoughts, the kind of variables that we manipulate with our thoughts and with language. So I call these variables semantic variables. And the kind of dependencies that exist between those variables is actually pretty particular. So what I'll be talking about today is part of a larger program of trying to take advantage of these assumptions these priors that we may associate with those variables. You see, most of the knowledge in our brain is not verbalizable, and some of it is. So that's the kind of division of system one and system two that I've been talking about in recent talks that this talk is also about. Now, there's the part of our knowledge which is verbalizable that we can reason and plan with, that we can communicate with language. And today I'll be telling you about that joint distribution between those concepts and how it can change in time in a way that may help us build better deep learning systems that can take advantage of these assumptions and priors. So this is really inspired by human cognition and the idea that machine learning really needs to put in inductive biases in order to gain generalization. In deep learning, we've already used a number of interesting inductive biases, but the kind of research I'm going to tell you about today is trying to add more inductive biases that are different from the ones we're already exploiting. And I have a list here of the kinds of inductive biases that this research is about. And in particular, in my talk, I'll be focusing on the red ones, which have to do with causality. So there's a notion that's very interesting in causality research of independent mechanisms, that the dependencies between these high-level semantic variables can be decomposed into small pieces corresponding to how different variables interact with each other and cause each other. And these mechanisms, which you can think of like the laws of physics, but at an abstract level, are what we would like to be able to represent. And many of these variables have to do with the things we name in language that have to do with causality often in some way. Agents, that could be the subjects, intentions and actions, which correspond to verbs, objects, which can be controlled. That often has to do with people or other agents doing things in the world and causing effects due to these actions. And one of the most exciting aspect of this point of view, so this is the third bullet, that thinking about it in terms of causality may help us deal with one of the biggest challenges in machine learning these days, which is how to generalize out of distribution, how to adapt quickly to changes in distribution. If you think about those changes in distribution in terms of interventions in the causal structure that explains how the world works, that actually gives us some answers about out of distribution generalization. So this will be at the heart of what I'll tell you about, and I'll talk about specific algorithms that are trying to take into account some of these assumptions. There are other aspects I won't talk about today, like the fact that these high-level semantic variables really correspond to thoughts and words and sentences. And so relating that abstract level of representation with natural language is also an important, useful thing we could add to put constraints on those representations. Another thing I won't talk about, but we have done work on, is how these mechanisms that relate these causal variables with each other, they're really generic. They could be applied to many instances, many objects of the same type, just like we do in programming with functions that can be applied to many different arguments that have a particular appropriate type. Another interesting area that we've been investigating, and that's connected to meta-learning, is the notion that a lot of that high-level knowledge is stable and has to do with the causal structure, while some aspects of it, which are due to interventions, can be changing quickly. And we would like to be able to take advantage of these different timescales and this notion of intervention and changes in distribution and how these changes occur. And finally, we also have work on how thinking about it in the way that humans solve problems and do credit assignment for learning can help us do it more efficiently. Okay, so first, the notion of systematic generalization is one way to think of how humans might be able to deal with out-of-distribution generalization by our ability to dynamically recombine existing concepts. And so this is connected with the idea that we have these relationships, these causal dependencies, but they can be applied and combined in new ways that allow us to deal with new objects we've never seen before, but that combine concepts we've seen already, even though these new ways may have zero probability under the training distribution. Humans are very good at that. But current deep learning is not very good at that, as we've seen in recent work. So one of the assumptions that is going to help us, I think, incorporate causality and generalize better out of distribution is to think about the structure of the joint distribution between these high-level semantic variables. And what I've been proposing for a few years is this idea that that structure is very sparse. So think of a sparse factor graph where the factors correspond to dependencies, those mechanisms. And what makes me think that they're sparse is to look at the way that we express knowledge with natural language, where something like a sentence is a statement that involves very few variables. So if I say, if I drop the ball, it will fall on the ground, it involves just, the ball, the ground, and the act of falling, and the position of the ball, right? So very few elements. And this kind of sparse dependencies are interesting and different from what we've been studying up to now in deep learning for the high-level variables, where we've generally assumed that they were marginally independent. I think this is too strong of an assumption. Instead, the kinds of concepts we manipulate, like ball and hand, have that sparse but still strong dependency structure that we need to take into account. So then the way to think about this is we have low-level sensory data like pixels and images, and we have these high-level semantic variables, and we have machinery like encoders and decoders that allow to map from one to the other. And so what we really want to do is to discover those high-level representations, as well as how to go from pixels to these semantic variables. So those variables are not necessarily given to us. And in addition to discovering the semantics of those variables as a function of the raw input, we want to figure out their causal relationship. So a lot of what I talk about is about discovering the causal relationships between a bunch of variables, in other words, discovering these causal graphs. One thing I won't talk about, but is also quite important, is where do actions come in all this? Actions correspond to changing things in that graph. You can think of them as special nodes that create interventions that change, for example, the value of a node. So one interesting aspect of this causal picture is that the interventions, the effective agents in the world, start with typically just one variable being changed. So in general, very few variables. So the change due to an intervention is going to be very much localized. Of course, then the effects of those changes could spread to many other variables. But the fact that the initial change is localized is something we can potentially exploit, because those interventions, if they can be explained by very few bits in the model that have changed, that means that we can infer what the intervention was or how to take it into account with very little data. So that means we can adapt to those changes very easily. Right? So, and that can give us a way to think of how, say, humans are able to do this fast transfer. If they have a good model of the world, then something happens, like I put on my dark glasses, that actually involves very few bits at the high level, just this one bit that says I put on my dark glasses, whereas there'd be many bits at the sensory level. Then there's a way for me to account for that change with very little data. In fact, a single example in that case, if I already have a fairly good model. And that means I can adapt to those changes more efficiently. But the argument we've made in a recent paper is you can take that story and turn it upside down and say, well, if having the good graph, the good dependency structure, and the good set of variables allows me to adapt quickly to a change when there is an intervention, then maybe we can go in the reverse direction. In other words, if I observe a change, if I observe a bunch of changes, the right kind of model should have the property that I can adapt quickly to those changes. And so that gives us a training objective, or at least some pressure on the right representations that we need to learn. So the kind of exercise we've worked on, and I want to describe it a bit more, regards discovering that causal structure from observational data where there is no change in distribution, no intervention, and from intervention data where there's a change in distribution. And although most work assumes that the intervention is known, that somebody tells you this particular variable has changed, we've been looking at the case where the agent observes that there's a change, but it doesn't know exactly which variable changed. And so you have to do inference over that change. So our first paper on this was published at the last ICLR, and studies the case where you only have two causal variables and you have potentially two observed variables, x and y, which give you clues about the causal variables a and b. And so what you'd like to figure out in this very, very simple scenario is A the cause of B or B the cause of A, and what's the mapping between the A-B couple and the X-Y couple? So in this work, we exploit only the speed of adaptation to the change in distribution due to an intervention on the cause, potentially the effect, but the one that really works well is on the cause, in order to learn what is the right structure of the causal graph. And the gist of how we can do that relies on the observation that you see in the figure, that with the correct graphical model that A is the cause of B, the adaptation to an intervention where the x-axis here is the number of examples after the intervention, the adaptation to this sort of new distribution is going to be faster when you have the correct causal structure, A causes B, than if you have the incorrect one in gray, B causes A. So now we can use that speed of adaptation as an objective, as a meta-learning objective, to guide the discovery of the right causal structure. You can also use that same objective to figure out the mapping between the causal variables A, B, and the observed variables X, Y. In our case, it was a very simple setting where the mapping is a rotation, and the learner only had to discover the angle of rotation, which it does. The second work I want to tell you about has to do with larger graphs. So we try to scale up some of these same ideas in the context where the number of nodes in the graph might be 5, 10, 20, 50. And the algorithm we have explored has three phases. In the first phase, we're going to try to fit the conditionals in the causal graph based on the data, the observational data. We're gonna have a distribution over possible graphs, and we're going to sample graph structures according to that distribution. The way that the distribution is parameterized is with a single probability for each edge to be present or not, each directed edge to be present or not. And then when there is a change in distribution, we're going to see how the graph that we have sampled performs. We're going to then compute rewards according to this gradient estimator in the formula here that allow us to increase the probability of the graph structures that work well, and then we're going to refit the graph with those new refit the causal model with those new probabilities. Now we don't want to have a separate parameterization for each possible graph because there's an exponential number of graphs, and so the crucial trick here is to use the same parameterization for all the possible graphs. So the building blocks here are these conditional probabilities that calculate the probability of, say, one variable given potentially all the others. Then the graph structure is going to select which of the others are allowed to be direct parents. Now, we don't know what are the direct parents, but we have these probabilities for all of the edges that essentially tell us which variable should be a direct parent. And so we can sample from those probabilities. You can think of them as masks, like dropout masks. So when we train, we're going to be sampling those masks, but the same MLP with the same weights are going to be used across all the graph structures. This is what really allows us to solve the problem. So we've made a number of comparisons showing that this actually works quite well in many different kinds of graphs. The row M here is the size of the graph, and the first row here is the name of those graphs, so different structures. And then the other rows here correspond to other methods that have been applied. So we can see our proposed methods is doing quite well. A variation on this theme that we have explored to be able to scale to larger graphs is something that we find in practice, that you may have a graph that is partially known. For example, in biology, we would like to discover the causal graph that relates how different proteins or different genes or different drugs interact with each other. And we might know some of that graph, some of these edges, and then for the other edges, we really don't know. So this is the kind of problem that we're trying to solve, where we're trying to apply our learning technique on just the edges that we don't know, and somehow the fact that we're given already a subset of the graph, it turns out that really helps a lot to obtain good results. Yeah, the other thing I want to mention in these experiments is the use of machinery to propose the correct intervention. So I said at the beginning that we're not assuming that the interventions are known, and when we know what the intervention is, we can actually do something smart about which parameters are allowed to change. So if variable A is going to be intervened on, that means the variable is going to take its value according to the intervention mechanisms rather than the normal causal distribution. So it's like cutting the relationship between its normal parents and the variable and introducing a different parameterization for defining its distribution. Then during the period of the intervention, we really want to not change the regular parameters for that conditional. We only want to change the parameters for the other the variables that haven't been intervened on. Now, we don't know what the intervention is, but we use a simple heuristic, which is that the variable that is predicted in the worst way according to log likelihood is most likely to be the intervened variable. Now, in the future, one thing we want to do is to actually use a probabilistic inference on the intervention. But that heuristic already brought us a lot of good results, as I've shown here. So on this, thank you very much.